So maybe while we're waiting, interesting note. So we had this poll, and maybe interesting for Elias and Suchi to know. So we asked people whether they use causal reasoning currently in their research, and let me see if I can still access it. But basically, the options were they use it actively at the moment. They did use it in the past. They are planning to use it in the future. They haven't used it and will unlikely ever be using it. And I guess that's about it. Or they don't know because they don't know how to use it. And the only responses we got was on I'm planning to use it in the future, or I don't know how to use it.
Rather, I would like to, but don't know how to use it yet.
Would like to use it, but don't know how to use it. So I guess that is probably describing best the motivation why we wanted to have this tutorial in the first place. It is so for people outside the MICCAI community. I know definitely Elias, and I believe Suchi is also maybe not attending MICCAI very often, but just to explain you a little bit that. So we had a look at previous proceedings, and especially also this year. So we looked through the 540 papers that were accepted at this conference, and I did a quick search for the string causal, and out of 550 papers, 5 papers had that string, but not in a sense of using causal reasoning. They were talking a little bit about some causal relationships. So you see this community is currently not a primary user of causal reasoning, and maybe that could be a great first question to both our guests here, Elias and Suchi. Welcome. I can see you now. Thanks for joining. We're really delighted that you could make the time. So we have about half an hour to discuss a little bit aspects of causality in the context of medical imaging, but also machine learning. The topic was pitfalls in machine learning. So my first question to you would be, do you think the MICCAI community is missing out? That we're not finding much work on causal reasoning in predictive modeling using imaging?
Elias, do you want to take that first?
Hi, Suchi.
Hi.
Yeah, I think so. I think that based on the talk before, and I don't feel, this is the thing. I'm not sure if there is an option. Meaning, I wouldn't put it as missing as something like what's the option, right? Usually, you are in the context of making decisions or having to craft some type of explanation, and this is invariably layer 2 or layer 3 type of statement. And given as discussed earlier, right? And usually most of the data is observational. Then, yeah, if you want to be principled and be able to provide some type of guarantee, we need causal inference methods. Then yes, I think they are missing out. And but I predict, if you want a prediction, that in the future they will be using that. The question is now how fast do you want them to be using the next 3 years, or you want to wait maybe the 10? And also how chaotic will be the process, right? Do you want to be more principled and try to leverage the literature that you have in the last, I don't know, 20 or 30 years, or do you want to reinvent the wheel or do things, whatever, not so principled, and realize later that perhaps the method is not doing what is expected to be doing, and then have this, whatever, and then start patching it? Then I would prefer obviously to be faster and to be in a principled way. But whatever, it depends on us, right? How efficient, or you guys, I guess, how efficient, but us, I'm including myself here, or Suchi as well, how efficient can we be in interacting with more people and in this community, let's say. Suchi, I don't know if you have anything to add, or what are your thoughts?
Yeah, absolutely. I agree with Elias. I do think I want to add a little bit to draw a bit of a distinction. So I think in the field, what I saw is, I feel like when many people are trying to understand how to build on or apply causal inference, the way people are thinking about it is, hey, is there a causal inference tool? Like, can you give me a causal inference tool or a methodology? And then can I run it on my data? And if I run it on my data, then can produce results. So as though they're thinking of it as like, I used to run methods A, B, C, and now these were machine learning methods. And now can you give me a new method, which is a causal inference method? And then I run that causal inference method. And now suddenly I'm in causal inference land. And that's, I think, one paradigm of thinking that many are mistaken to think is naturally the way to think, because when you're an empiricist, you think a lot about like, well, I have a problem, what can I do to solve it? And you're looking for increasingly more and more tools in your chest. And here, I think fundamentally a different approach is needed. And the different approach has a few different pieces to it. So the first is, I think, when I spoke a little bit about robustness, in where, as we're trying to think about transportability or generalization, robustness, reliability, like all these, there are different topics, like, or estimating effects, like there are all sorts of places where, to varying degrees, knowledge of causal inference impacts the type of solution you might produce. So it's not just I'm using a causal inference method or I'm not using a causal inference method. It's more that by having having fundamentals in causal inference and having an understanding of causal inference, and more importantly, even one level below that, having an understanding of your data and of facts about your domain that are causally true or not true, or facts about your domain that are spurious associations, that way of thinking is actually more necessary. And when you have that way of thinking, then you can integrate that thinking in terms of how you're going about building, employing, validating, drawing conclusions from your approach. And what I found in some of our, just kind of both watching we work in the community, but also our own work we've done in the last 5 to 7 years, there are people where they come in from this belief in the machine learning community, or when you're working on hard applications, that, hey, my data is really complicated. My world is complicated. I just can't, are you telling, but to apply causal reasoning in any form, I need to have the causal DAG. And I can't have the causal DAG, therefore end of story. I don't have anything, so I can't be using causal inferences anyway. I think what people are fundamentally missing is that what you really need is, in order to solve problems, in order to make conclusions, you need to understand what are the assumptions under which you're operating. And understanding those assumptions is really, you're better served when you have a little bit more fundamental understanding of your data and this causal way of thinking. So that's really sort of, to me, the most important, like, you should take intro classes, you should get a sense for, what does it mean to have fundamental assumptions to be true? And like in our work in robustness transportability, what we often find is you leverage ideas from causal inference to build novel methods that are integrating causal inference and machine learning in order to be able to give robustness guarantees or reliability guarantees, in order to build methods that are more sound. And so answer is not causal inference method versus machine learning method. The answer is integrate causal thinking into, machine learning, where you're able to work with very large, messy data sets, and then that integration kind of produces your ability, and integrate in many ways, variety of different ways, all the way from cases where you're fundamentally advancing causal inference methods by using advanced techniques in machine learning. Alternatively, you're bringing causal reasoning into stating the assumptions more clearly in machine learning. But all of that now leads to better, higher quality work.
So if I understand correctly, what you're saying is using causal inference is hard work.
Oh, I mean, anything to do, like even machine learning is hard work, but you're right in that to do it correctly is hard work, yes.
So going back to the poll and the people who said they would love to use it, but they don't know how to. How are we going to help those people?
The hard work of how they use it, and building here what Suchi is saying, I think is that, there's these people that say, perhaps I need the causal DAG, but maybe it's very hard in my master domain to have it, right? And a lot of the results that we discussed, we show that without the DAG or without these assumptions, without some assumptions, you cannot make it. This was the whole talk, right? Now the question, like, what are the assumptions? Then Suchi is saying, maybe there is the causal DAG. True, it turns out to be the sweet spot, in my view, representation today in 2020 about how we articulate these assumptions of these structural constraints that we need. But now there is also the people are asking about open problems. The third one that I would say, I already mentioned two in the previous one. Third one is like, how can you relax these assumptions? Nowadays we know that the causal DAG is a way of organizing it. But now is there any other type of object that could encode maybe not every information that the causal DAG is encoding, some type of equivalence class of causal DAGs, and that will allow us to perform the task that we are trying to do? Then I think there is energy, as related to Kayan's question as well, about having side information, right? Can you combine experiments? Can you combine substantive knowledge in some way that is not so rigid? Now, the most statistical literature assume that you need a randomized control trial to do traditional, that you need to do the causal, to make the causal statement. The most traditional or strong causal inference way of thinking is like you need a causal DAG in order to do that. And the causal DAG is encoding all these assumptions that you need to know all of them based on substantive knowledge. How can you have a mix about not having the full experiment, but partial experiments or a subset of the experiments together with the subset of all this knowledge that is encoded in the DAG, such that there's this mixed kind of DAG that allows us to play the game. And it be evolving also. It's like the DAG is just contingent on the time. Maybe tomorrow we have a more refined version if the one today is not enough based on the principles to infer what we want. Then I think having this object that is a relaxed version of the DAG is, I think, a topic of high interest. And we should consider it more. It's not not binary in some sense.
And I think I would like to add something to what Suchi said. I think one thing that's required is the education to what Suchi said, that like, you start thinking causally. But also another important thing is that because the focus of the field, I mean, probably the progression has been on a level one, like a lot of prediction. And the focus has been shifted toward like beating the benchmark. Like, I mean, the X input, output, and try to do association, beat the benchmark. And this basically shifted the community a little bit toward like avoiding actually modeling this messy data that needs, considering information from multiple resources. And in order to do that, you cannot avoid causality. So I think that's another thing that needs to be encouraged, that if you have a messy data, don't simplify it to a bunch of prediction. Try to model the data collection process, as you mentioned in your talk. Try to model the way that the data is generated, the labeling is, annotation is generated, and also all kinds of, if you need to increase the sample size, and then you have to collect the data from multiple hospitals, you have to be cognizant of the fact that there will be all kind of shift, prediction, and that in order to model that, you need a causal thinking. So part of that goes to education as well.
Right.
So I think around education, the question is, part of the challenge, I have to say, Elias, is the causal inference community has not done itself any good by infighting, fighting on terminologies, fighting on different boot camps about A versus B. Many people are saying the same things, but they love inventing terminology of their own. So personally, when I felt 7 years ago, when I was starting to get to learn, I was like, all right, I need to be productive. I need to go learn and figure out what is it, how can I learn the basic tools so that we can start being more productive in using these ideas in machine learning. And the challenge I felt at the time was that it felt like I was going in circles, kind of learning, reading papers from these various different camps, each contradicting each other, as though they were really contradicting, but they weren't contradicting. They were just criticizing each other's terminology and framework. But in reality, many of the ideas are actually pretty much the same. So a practical shortcut for new people who are coming into the field, if I had to lay out a practical shortcut to summarize kind of what I found to be most productive, I would start by sort of finding 1, 2, or 3, or 4 papers on this notion of like, and obviously I'm not going to do justice because And I'm coming at it from a machine learning standpoint, right? I'm thinking of it as like, there are people who love doing machine learning work. They want to be productive with data sets. They want to solve real problems. They want to invent methods in order to help them solve those real problems. And that's the goal. So if you want to do that, then I found the things that I found to be super helpful was, first of all, you have to have some kind of knowledge in representation. If you don't understand representation in any way, you're in trouble. Now, I was in a good place because I started from, representation, like some kind of graphical approach to representation is very intuitive. If you love joint distributions and writing them symbolically, more power to you. Structural equation models, a different way, more power, like whichever one of these makes sense to you, you should use that. Many people in machine learning mistake graphical representations for using probabilistic graphical models as their modeling framework, which is a false dichotomy. Like in reality, you're thinking of some kind of representation language. To me, visual representation languages are really useful because you can communicate with other people beyond your own field. So graphical languages are really simple, intuitive, easy to understand, but it's just representation, some language for being able to say, what is the data? How are they, what data are you collecting? What variables are you collecting? How are they related? What are you trying to model? Some way you need to be able to think about that and talk about that. And graphs were a really good, easy way to do that. So that's like step one. Step two is, so if you can learn graphs, then the step two I would do is go learn a little bit about potential outcomes. Why? Because it's the closest thing that it starts from a very estimation-based mindsets, which is where machine learning researchers sit, and brings some causal thinking into thinking about potential outcome framework. And, we wrote several papers on using this potential outcome thinking with machine learning to start thinking about treatment effects from messy data sets and laying out what are the underlying assumptions that allow you to estimate a certain quantity, like can you estimate effects or not in certain data using, and building really powerful machine learning tools for estimating effects. But at the same time, you were integrating causal thinking in thinking through when something was possible to estimate, when something was not possible to estimate, really simply. So like that is like a very nice, beautiful intersection where it's super easy to think about, learn about the potential outcome framework. You can apply very powerful methods to it. And so that's like step two. And then step three, you start now expanding your tool chest from there and expanding your tool chest to learn about, depending on what your goals are, where you want to go, there's like methods for doing discovery, structural learning. So that's like you have messy data, but you don't understand like what is or isn't true in the data. You can go talk to experts, or you can employ methods for doing causal structure discovery, right? So the question is, why do I care about causal structure discovery? This is so if you want to learn about the data in a lazy way. So I want to learn about my data, but I don't want to learn about it from scratch. So maybe I can take my data set, apply some causal structure discovery work. It gives me some graphs. I can start reading those graphs and learn what is or isn't true in my domain. And now that gives me some language to start talking about what is or isn't true. And we use that all the time in doing work on robustness. So as an example, when we think about, we've built a method using dataset one, we want to be able to apply in the real world. We want to be able to talk about either building learning methods that are more reliable or robust. So in other words, give guarantees against certain kinds of underlying shifts in your data distribution. We've employed all these causal learning, we've employed ideas from causal inference to be able to build more robust learning techniques, right? So that knowledge of your causal DAG and can be employed in order to build learning techniques that are more reliable or robust. Or alternatively, you can use that same kind of knowledge to start giving you, for a given method, given a data set, you can start quantifying how robust is it. And there are whole new lines of work on measuring robustness where you bring in causal thinking. So I think, to me, the step one, learn what a DAG is, some graphical formulation, some graphical representation, being able to think so that you understand this notion of a data generating process, assumptions, dependencies. This is not intimidating. It's literally like 1 or 2 introductory classes on Coursera. And then second, using that to learn something about potential outcomes framework, very nice intersection. And then, pick a couple of problem areas where you can start to see how the two get integrated. And estimating treatment effects with potential outcome framework is an example. measuring whether something is not, reliability and robustness and transportability is another example. And, I'm happy to point to tutorials in the field or ideas in the field, like simple tutorials you can follow in that area to kind of see how the two get integrated.
That's wonderful. Actually, it's super nice to hear that what your suggestions are, how they align with our first session this morning, because we actually had an introductory lecture by Kayan on probabilistic graphical models. And then we had an introduction to the potential outcome framework by Christine. So maybe those two want to add something. So so either you have read our schedule.
No, Ben did not pay me to say that, and I did not get any primer ahead of time. That is genuinely how I felt. So that's awesome.
That was like point on, like exactly that's the direction. I guess like we are probably coming from the same background. I was Ben Tasker as a student, so it's basically the same thing. I mean, although I have to criticize the other side as well, that in the probabilistic graphical model field, the emphasis shifted too much toward inference, and this is why probably for many years people ignored the fact that some of the causal question at least can be answered. I mean, if not all of them, are so much of the hardness problem. But anyway, so yeah, I'm happy that these two are eventually merging.
Let me just as a technical person in the meaning, I'm working causality. First comments about the discussions and people personalities. There's no way that I can address that, Suchi. You can, and it's your own rant. And each person have their own personal, based on who they know and how they started and so on, then nothing to comment. I prefer even not to share, because it doesn't matter what is my personal opinion about what persons are talking bad or well about each other. But anyhow, it's a psychological observation from you, I guess. But on the more concrete side of the technical one, I like your suggestions, but there are some caveats. I wouldn't say, I think it's slightly misleading. I come from the same background, I think, as you and Kayan about the probabilistic graphical models or graphical models broadly, but it's misleading to say that or apparently to suggest, this is what I got, that, that's all what we need. The whole talk that I gave in the last 1 hour and the whole endeavor by Pro starting in 1989 or 1990, after when you start learning about graphical models in its modern form, Bayes nets was one of them, and you have the Markov random fields, MRFs, and the other was about all the machinery that we built to talk about condition dependencies is not sufficient for causal inference. Then to say that, take a course, one course or two courses in Coursera graphical models, and you're in a very good shape to do causal and you got something about potential outcome, I think is as a professor, right? As someone that if a student comes to me as a misleading, because there is so much, there is 10 or 15 years of work about how to restore the semantics of the graphical models in order to do causal inference. Then my talk was about that partially, and I'm sorry that you're not here. Hopefully you can talk more. And I shared the paper, by the way, in the chat. But the point is like the sentence, the summary, like not all graphical models are created equal. And the key here is about how do we find a good graphical model that is encoding, as also alluded in the morning many times, the type of constraints or the type of assumptions that we need. The traditional graphical models are good for condition dependencies. We need other constraints in order to make causal statements. Then technically, that's what I would say. Obviously, there's a lot of good people doing good stuff in the potential outcome. My experience of teaching as a professor is it's harder to teach some people that came from the potential outcome because they believe that they already know. Then my preference is to get students that don't know anything. We teach in the right way using graphical models, by the way, as the baseline, the causal graphical models, and then I connect in many different ways with potential outcome later. I think it's much, much easier. And what's the issue? As you say about representation, I like your point. The question is about what is a good representation. Potential outcome is not a good representation to think about for something. Then
but 1 second, Elias, this is important because I think people in the machine learning community are coming from like a lot of, like there are some baked assumptions and baked knowledge, right, that we're building off of. So I don't think potential outcomes is a good representation framework. So just everybody clarify, I don't think people think that. So I think you may think, I don't think people think that.
People think that. What do you mean?
People in the machine learning community do not think that. It's possible people in the causal inference community think that, but I don't think that's an issue in ML. I do think when you say this thing about different graphical models are, not all of them are good, 100%. But I think we should clean up language there. So when people think, I think the important part here is the graphical representation. And then a model is separate from a representation, right? You use a graphical representation, using a graphical representation, and then a particular way to estimate and a particular objective function and a particular training algorithm, you can come up with a model. But model, like people have mistakenly in machine learning attached graphical representation to a graphical model. Like a model can be represented graphically, a model can also be represented symbolically. So to me, the two are separate, disparate. Yeah.
Let me just one more bit of history. Why people like in the 80s, including your advice, why they like graphical models at some point is like, or in the 80s, starting in the 90s, because this is a parsimonious representation of different type of constraints that allow us to do probabilistic reasoning. Then the graphical model, this is the insight. The graphical model itself is playing two roles. One role is representing the assumptions or these conditional independencies that are sufficient to layer one of probabilistic reasoning, and also it serves as a device to do computation in the model. And then you have the whole literature on belief propagation, and all models, even the model ones, are based on that in some form. Now, the model is representation of knowledge, but also serves as a computational device. That was the attraction of the base nets or any other graphical model. Now, the discussion here is like, for causality, the only observation that I made is like, it's not sufficient. We did this additional assumption. But I still call, this is the causal model. This is a causal, it's a parsimonious, it's not a structural model. This is the whole talk. It's not a model in the details as the physicists, but it's a parsimonious representation of this underlying collection of mechanisms. And it is an encoder of the assumptions. Now, that's point one. Point two, in causality at the moment, this model is still not used to do inference, or not in generality. I cannot get the causal graphical model and do inference with 1 million variables, because there are issues about latent variables and so on. There are technicalities that we didn't connect, as it happens in the probabilistic inference literature. But still, it is a model, and I'm not sure. It is a model of the assumption, and it is a nice language to describe the type of invariances that we need to do this type of reasoning. It sounds good for me. I'm not sure why you don't like the word model. This is my point, but I want you to conclude, because Suchi started giving recommendations for the student. It's very important to me. My suggestion for the student is that I think the best introduction, by the way, I'm not happy with the material. I think the state of education, even 20 years after you understand in some way, it couldn't be worse. It's so bad in terms of causality. Then I'm very sad and acting for that. I have been writing internally to try to have material, but this is whatever, it takes time. But I think it's terrible. But my recommendation nowadays is based on what is available. I usually recommend the Book of Why as the first, because it's very nice and general introduction that even my mom, that is not a scientist, can understand and get excited and motivated about the problem and get a little bit of the history. And then the suggestion after, the only books that there is some level of consistency, or more consistency, is the books by Pearl. I would say the primer book, that is a good one, that is a very short book of 200 pages. It's called Causality in Statistics, I think a primer, by Pearl and Jewell, a professor in Berkeley in statistics, and Guy Moore, that is the daughter of the Clark Guy Moore that was alluded earlier. I think is a good introduction. And then you can go to Causality book, which is a slightly harder book to read, in my opinion. It's very good, but it's much harder. Then I do think it's bad, but these will be my suggestions in terms of material, that it imposes a good bias, that my experience allows people to get the big picture and understand what is really happening and what's the relationship, and even a little bit about why there is some of these discussions, why there are personalities. It's not that it's also not, I don't think that it's true in my opinion, but technically that they are just discussing with each other, it's just exchange of words. I want to call my name potato, you want to call potato. It's not that. Between some of the guys, there is serious discussions about this type of assumptions and what these models are encoding and so on. That is quite technical discussions in reality.
Great recommendation, Elias. I know Suchi needs to leave soon, and we promised this will only take 30 minutes, but I see there's so much more we need to discuss. Unfortunately, we couldn't take a lot of questions from the audience. We tried to bring in some of the discussion we had earlier. It seems there needs to be a follow-up. So what we are trying to promise is till next year, we want to turn this tutorial into a workshop. I believe it's the time that we bring to the medical image community another platform where they can discuss this type of issues. We would love to invite you back for a follow-up discussion. I know you're both very active on Twitter, so I hope that people can reach out and ask questions on Twitter, and I'm sure there will be an active follow-up discussion on this. Suchi, thanks so much for joining this. This was really insightful. Elias, thank you for spending almost half the day with us, giving this talk and also this panel discussion. This was excellent, and thanks everyone for joining, for the questions that came in. We will make sure they get answered one or the other way. Thanks everyone.
Thank you all. This was fabulous, and look forward to following up.
Thank you, Suchi. Thank you, Elias.
See you. Bye, guys.
Bye.
Thank you.